Okay, so we've done a good exploration now of this slant-stack operator and or slant-stack transform. It's a wave field transform, line integral through the wave field, and as we'll find out later, it works as a line integral through any scalar field, and we can develop it into tomography that way. And then this slant-stack operator is then represented in discrete form using these L, K, J, I integers and the corresponding spacings or intervals in ray parameter P, so that's dP, dt in time, dx in x, and there again is dt for time. So we've taken a look at what that does, and I'll lecture to you a little bit tomorrow about taking the slant stack into the Fourier domain and what you can do to that. That was developed by Thorson and Claerbout many years ago. And so then we went to consider a very simple data set. And let me see if I can bring that up. Yeah, there it is. We know how to forward and inverse or actually transpose slant stack it. We explored that pretty thoroughly, and it worked better than I had any right to hope. And then we took a look at the surface wave in these records, there's you know, a very coherent surface wave, very strong. It's the strongest part of the data set, but it has different, very distinguishable phase velocities at different frequencies. So in the middle is the same record, which is the second record in this set, which is filtered down to 4 Hertz, and so it only contains energy at 4 Hertz and below. And on the right, the record only contains energy at 14 Hertz and above. So we can notice. So with the energy group timing, you can get the group velocity, and you can look at group velocity versus frequency, and you can get information about Earth structure that way. And that, in fact, is how the latest station-to-station cross-correlation, microtremor cross-correlation work is done. You take two seismograms, they're full of random noise, but they're simultaneous. Maybe they're both a month long. You cross-correlate them, and the very first, and we discussed cross-correlation in 706, the very first 10 seconds of that cross-correlogram will be as if you had a source at one station on the surface and a receiver at the other station. Okay, and that's called an empirical Green's function. It's as if you had an impulsive source. And there's a lot of interesting papers about empirical Green's functions and why they work at all. The same idea has been developed in exploration seismology as the idea of virtual sources, and there's a couple of books on that now from the SEG. It's a way of putting sources where you didn't have them before, and it's actually possible to develop quite a lot of new information by cross-correlating the traces you already have. And that's a topic that I can lecture about if it's of interest. So that's that's how this sort of thing is exploited earthquake seismology, by looking at the group velocity. But as I was pointing out last time, the slant-stack is really good at finding that phase velocity. Okay, which if I make picks along the the positive to negative let's see, I think I've gone off here. Let's see. From negative going up to positive, I'm following a certain slope, a certain velocity. So if I make those picks in the low frequency version, and then I make them in the high frequency version. Alright, so I'll make picks in the high frequency version. And you might be able to see, since both of these sections are at the same time scale, the same exaggeration, that it's a slower velocity, a lower velocity, a steeper slope that follows phase, say if you're following down the center of the black or the center of the white or following a zero crossing. It's a lower velocity and steeper slope at high frequency and a higher velocity and shallower slope at low frequency. And that ties in with Earth structure. The low frequencies are sampling deeper into deeper below the surface, and thus typically encountering higher velocities. And so that's dispersion. So what we want to do is use the power, as we've seen, of the slant-stack to find, to assess and estimate phase velocities. And so here I have two phase velocities at two different frequencies, and that's 2 points along a dispersion curve. Okay, and I need more points. So do I have to filter this 50 times? And make picks and calculate slopes in each time. This making picks at different frequencies, that's called it's related to the plus-minus method in global seismology, and it's a time-honored way of looking at phase velocities and phase velocity dispersion. But with refraction microtremor, there's a much easier way. Okay, so we go back to my 2001 paper. We've transformed the data from its original x and time domain to p and tau, and we actually do it, of course, using this discrete equation. And now we're going to transform it again. So we take the p-tau data and we transform it with a one-dimensional Fourier transform from tau to frequency, and here it's represented as a frequency f. And so the integration is along tau, and you can see here as you saw in 706, those of you who took it, you see the Fourier kernel, as it were. The Fourier exponential for time to frequency, and here instead of t we have tau. That's okay. And we're not, we have traces at constant p, constant slowness here, and the traces, as you go down the trace, tau increases, and so it's really it didn't seem like much of a conceptual leap to me to just Fourier transform each of these slant-stack traces into frequency. So instead of and you can see why if you remember the Fourier transform equations from 706, it was just minus I omega times t, and I wanted to use frequency here in cycles per second instead of radians per second, so you have to multiply by 2 pi, right? Because omega is 2 pi f. So that's the only difference here. And then we discretize it, okay? So you know, we already know how we discretize p, so I'm not going to show you that in equation 4 down here. But now the frequency f is integer m times the frequency sampling df. Okay, so you know, we got to sample frequency evenly, just like we've sampled time evenly, just like we've sampled slowness evenly, sample p evenly. And here's the time sampling. Tau is equal to the index k times dt. And then here, you know, you've got to have k times dt instead of tau, and you've got to have m times df instead of f. Okay, so that's the only complication there. 2 pi is still there and all that. All right, so let's do that. Just have to go back to UMAT, and let's see. Do I have I have an inverse slant stack here. Okay, so I don't want that anymore. Let's go ahead and slant stack this data set again. Let's see, slant plane. All right, so let's see if we can remember the best slant stack. We wanted to go ahead with 100. Maybe I'll go up to 120 different samples of p. We've got some lower velocities in the second section here that we're seeing. And we want dp. Okay, so now here's the question that gets asked when you do a ReMi analysis, you know, just straight out. Okay, we're starting at p0 equals 0. Okay, so we're going to start at 0 slowness. And what velocity is that? That's of course infinite velocity, right? That would be simultaneous arrival, which, you know, some data sets have it. Like at the top of a reflection hyperbola, you've got a simultaneous arrival, 0p. So got to have that in there. As you increase p, you decrease velocity, right? So our question now is, what is the lowest velocity we want to analyze down to? Okay, and you know, to be perfectly safe, and knowing something about this particular area where this, in Dixie Valley, where this data were taken many years ago, there are some hints of velocities down as low as 100 meters a second. So we want to make sure we get down to 100 meters a second. And so that means we want our maximum P to be 1/100th of a second per meter, right? So our maximum P is at 1/100th of a second per meter. So that means I want to take 0.01, and I want to divide it by 120. Okay, and then now that's the P interval I'll use. So that's 8.33 E minus 5. So I'll enter that. Okay. We'll go ahead with the slant stack. Okay. Stretch it out. Let's see. Times 2, and then, all right, so 2 times vertical exaggeration, and then we view it at 150%, and we flip the amplitudes at 3 times RMS. Okay. So, and that's the second record, which doesn't have a lot at the larger P's on the right side. But the first record has more, maybe. Although you can see it's kind of, it's maybe getting a little repetitive out there. And so we can see the refractions way over here at near zero slownesses, you know, higher velocities. The reflections are in there too. Some good hints of ellipses in there, you know, sort of down here. And climbing up to these intermediate velocities. There's the velocity of the surface wave, which is really what we're interested in here, and seeing how that changes with frequency. But you know, it's pretty hard to interpret this this slant-stack. All right. You know, we did some filtering the slant-stack domain, trying to emphasize the most powerful, in other words, the most linear arrivals, and all that is easy enough to do. But let's see. So we could do a Fourier transform, and then what do we? You know, it's a complex Fourier transform, so we could plot the real or the imaginary part. But really, what we want to do is we want to plot the power spectrum, right? We want to know where the energy is. You know, how much energy is traveling at what phase velocities at what frequencies. And so, you know, according to Claerbout's definition, you get the spectrum, the power spectrum, by just taking the Fourier transform. So F sub A is the Fourier transform of the slant-stack. Okay. So F sub A of PF. And you take F sub A of PF and you multiply it by its complex conjugate, and that's basically squaring the value, the complex value of each frequency component, and gets you the power. Okay, so and in fact, as you can see, I don't really write that out in discrete form, because in discrete form it's really the same as it's exactly the same. You know, there's no summation here or anything, so it's exactly the same as. The discrete form is exactly the same as the continuous form. So, you know, equation 5 would be the same either way. Okay, so in UMAT, you can go directly to the power spectrum. You, in fact, don't even have the option of doing the Fourier transform alone. So we'll take this slant-stacked result here, and we will compute the power spectrum of each trace at each trace, of course, is at, you know, each column in this plot is at values of constant slowness. Okay, so we're going to get one spectrum for every one spectrum for every every increment of p. Thank you. Okay. Yes, and it's going to, so instead of the vertical axis here saying intercept time, it's going to say frequency.
That's the part I'm having trouble understanding. You're switching from, I don't understand what's the relationship between the frequency of these influxes and velocities that you can mathematically...
See, there's no relationship between the velocity and the frequency, because the velocity you look at across different traces. Whereas the spectrum, take a look at this, say equation 3 for the Fourier transform. Notice that we bring in the data, at every different value of p. But the transform itself, the integral.
Yeah, you're acting on.
P is not. Yeah, p does not come into it.
But that was what I should have asked. What is the relationship between the frequency of one of these impulses and the time variability at t or
well, that's what we're going to find out. Okay, just by we're gonna look at I didn't really think I didn't think very carefully about what that relationship was until I made my first PF plot and actually looked at what happened to the data. Okay, that was really key in my in my invention of the refraction microtremor technique. I mean, I could theoretically see what you would do, and with the codes I had, I could carry out the process. But until I started looking at PF plots, I really didn't understand it. Okay, and I didn't really understand what the PF plot was actually showing me. Okay, and the PF plot was originally developed, let's see, it must be on the next page. Oh, yeah. McMechan and Yedlin here. They're the original developers of the PF plot. All right, and in my first version of this paper, I referenced McMechan and Yedlin, and I had no equations because they had all the equations in their paper. And the BSSA reviewers said, "Well, how can you do this? We want to see some equations." And I said, "Okay, McMechan and Yedlin published all of them, but all right." So I'll throw in the equations. So now I went from 0 equations to 13 equations because I put in all the discrete ones as well. So yeah, let's try to figure out, in this data set, which is fairly simple, right? I mean, there's really one Rayleigh wave in here. We know where it comes from, and what happens to it. All right. So, instead of looking at time at every different slowness, we're going to be looking at frequency and the energy at each frequency. Okay. Well, how do we do that? So let's go ahead and do it. That's power spectra. It's going to take the power spectrum of every trace in time, and it's just verifying for us that the DT is okay, which it is. And the first thing you'll notice here is that there's practically nothing in the plot. Oops. So what's going on there? Okay. And so the purple color is essentially 0 amplitude compared to the any other color. If you look at the color bar down here, the purple is 0 amplitude relatively. So there's a little bit up, way up against the top of the plot, and that kind of makes sense. Okay, the sampling, what is this vertical axis now, the frequency axis? Okay, notice we really have, this really is exactly the same slowness axis, right? 0 to 0.01, right? That's pretty close to 0.01 seconds per meter. Okay, across the top. Same direction, everything. And you might notice that that the traces, you know, where the first arrival, I mean the Rayleigh wave, you know, slant stacks into. I mean, that's where we're seeing. That's the only place right now where we can see anything in the spectrogram of the slant stack. Let me play with the. Let's see. This is clipped at maximum. Yes. So let me clip it at RMS just to see what's there. Okay. So what we can see is that there's other colors, you know, non-purple colors, you know, jammed up against the top of the plot. So there is something at every different slowness. Okay. There is something at every different slowness.
But you've got to comparatively narrow down the frequencies.
Exactly. Okay. And okay, what is this bound here? Well, it's the Nyquist frequency, right? It's the highest frequency that this data set can represent, because the sampling frequency is 1,000 hertz, 1,000 samples per second, and so the Nyquist frequency is going to be half of that, because you need 2 samples per wavelength. The highest frequency that this data set could represent is 500 hertz, and there, you know, there is something in there. If I, you know, if I clip it at, you know, 1,000th of the RMS, yeah, you know, there's something in there, but you can see it's mostly just junk. There's some airwave noise. There's other stuff. There's obvious artifacts. These, you know, anything that's rectilinear in these kinds of plots, I automatically just. Yeah, so you know, most of the spectrogram, you know, at the higher frequencies is pure junk. I'd be perfectly happy to throw all that junk away and just to be able to look at what's you know, what's at the frequencies I'm interested in. And here's another consideration. We're interested mainly in some fairly low frequencies. Okay, why is that? You know, considering the nature of the surface waves and what we're trying to determine, for engineering reasons, our objective here is to look at shear velocities in the upper 100 meters, maybe the upper 5 meters at shallowest. Okay, and so those tend to, you know, those would be wavelengths of, you know, maybe 20 meters, and you know, you can use V equals F lambda to convert from wavelengths to frequencies, you know, given a certain velocity. So let's think about it. If we think the shear wave velocity here is about, as we measured from the Rayleigh wave, let's say it's about 200 meters a second. Okay, and we want to see, you know, we want to look at wavelengths of 100 meters, thinking that that's going to give us information, you know, at least down to 25 meters. Okay, so F is V over lambda, so the velocity is 200 meters a second. Lambda is 100 meters, so F is 2 hertz. Okay, very low frequency. I mean, it's all of our reflections are up at about you know, 50 hertz, 100 hertz. Okay, very low frequency. So you know, we're really interested in just the lowest frequency part of this. So you know, let's be well. Actually, if I make some picks on this, I can see the frequencies. So we're seeing, you know, prominent energy, and there's the frequency down, you know, at 40 hertz, and then down here, I mean, there's really nothing at. so nothing below 50 hertz. Let me mark here. So that's, yeah, 200 is about 49 hertz. So, okay, I thought, all right, I can't see anything in here. Let me throw away this data, then I can expand the part that has, you know, some information in it, and maybe I'll be able to see something. Okay, so I'm going to cut out the first, you know, the first samples are at the top, and you go 200 samples down, and you get to the end of where there's any information. All right, and that's you know, it says here 200 samples is at 50 hertz basically. So I'm going to cut out the first. Oh, actually, I think I can cut it in hertz. So let's go ahead and do that. And that's a method called cut time. Okay. And actually, before I do that, I got to make sure I don't make the mistake of looking at only one of the sections. Okay, so there they are. And yeah, maybe there's something slightly above 50 hertz here, but I'm still gonna first try removing everything down to everything above 50 hertz. Okay, so I'll go to cut time, and so I want trace to start at 0 hertz, but I want them to end at 50 hertz. Okay, and now I need to adjust the viewing of this thing. Maybe I need 5 times vertical exaggeration, and I need, let's see, what am I zoomed to? I'm at 100%, so I can zoom it to 150 again. So there's this sort of double structure here. So we have slowness running to the right and frequency running down. All right, and that's not the usual. You know, that's a way of plotting reflection data, right? Which is okay. So in the plot parameters for the spectrogram, the PF plot. I uncheck rose point down. Positive amplitude only is good. So let's apply that change. And I like to look at sort of you know, screen-shaped windows. And you know, you can see things are kind of they sort of look stretched out vertically to me. So I'm going to adjust the vertical exaggeration here. Maybe 1 even. Yeah, that's pretty good. And there is, you know, there's plenty of choppiness here, but there's some major features we can interpret. So I'm going to clip it. Let's see. Let's try 3 times RMS. Yeah, that's pretty good. And these are the major features. So you know, essentially, we've taken this whole record back here, and we've transformed from X to slowness, which is now vertical. We transformed from time to frequency, which is now horizontal. Okay, and you know, let's figure out what we've got. So, for instance, if there was an air wave in here, it would be at high frequency, and you know, that may be what we're not looking at. Oh, I'm looking at the first. Okay, here's the record we're looking at. Okay, so the air wave would be at high frequency, and it should be at a very particular velocity, right? The air wave should be right about 330 meters a second velocity, which, let's see, this is 0.01 at the bottom. That's 100 meters per second. So if we go halfway up, that's 200 meters a second. If we go halfway up again, that's 400 meters a second. All right, so I can sort of mark those. Right, I'll put a pick here. That's at 100 or 200 meters a second, and go about halfway up again. That pick is at so just guessing, you know, airways at 330 meters a second should be, you know, up in here somewhere. And there's some candidates at the higher frequencies. You know, the airwave is not very visible here. The thing that's really visible, of course, are the S waves and the Rayleigh wave. You know, if we gain it the same way, you know, that's kind of all we're seeing. Now let's see, the refractions are at let's see, I think if I remember right, they're about 2,000 meters a second, and you know, they've got kind of a moderate frequency. You know, I think these are maybe 20 or 30 hertz. And so that's let's see, 200, 400. You know, that would be 800. That would be 1600. So the refractions ought to be jammed up against the top, and they're at a moderate range of frequency, and there they are. Okay, kind of these drawn out spots. Okay, you know, that are not purple in color. And actually, I like a different color table for this. Let's see. Maybe the best I can do right now. Okay. So now, okay. There's sort of two main red spots in this. All right, and they sort of correspond to the two main things we can see in the data. Right, there's the first arrivals and the multiply reflected refractions there. Okay, they're up there. And then there's the Rayleigh wave, all right? And that's up here, all right? How do I know that? Well, in my 492 class, you know, I have them get the frequency of one of these waves. The geophone response is falling off below this frequency. Let's see what frequency that is. Well, yeah, 4.5 hertz. That's half the this data set was recorded with 8 hertz geophones, so down below half of that, you know, the response really falls off a lot. But you can see there's some hints of some stuff in there that's kind of, you know, lining up in a way. So if I underclip it, like at RMS, yeah, I can see that a little bit better. So, you know, maybe that's something too. All right, but I can't see it very well because it's so much lower than the sort of loud stuff over here. You know, this is following a curve. Okay, and the curve in general goes from high velocity at low frequency, upper left, down to lower right, which is lower velocity at higher frequency. Okay? And so is that a normal dispersion curve? And actually it is. Okay? That's a perfectly normal dispersion curve. There's two confirmations here. I mean, even just from looking at these data sets, you can get the predominant frequency of this data set right here on this plot. You can get its velocity at that predominant frequency, right? And that lands as a point right about there. Okay. And that's 12 hertz and 0.04. That's 250 meters a second. Okay. So that's in there. And the other confirmation is that we already decided from this data set that velocity should go up with or should go down with increasing frequency. Okay, and here with increasing frequency to the right, the velocity goes down. Over here it goes down very quickly, and then it goes down less quickly. I added to this several, this plot basically is what McMechan and Yedlin had. Okay. And they showed